Let's see. I'll do share screen on my side and just do the loading
That's okay.
while you figure that out. Okay, we are live. And I'm just going to be on the Rapids Academy homepage while folks trickle in. And Matt, just give a shout when you're ready to go. And then I'll switch over the screen over to you.
Do you want to do anything while we wait, Leo? Presumably after the hour, sort of wait for a few minutes. Is there some like light activity that you tend to do?
You're muted, Leo.
Oops. Great. I'm about to get some reverb here. Let me help with a bit of an announcements, and then I'll jump back here. In a few minutes, you might want to just tell folks to point them to the Slack channel and just kind of tell folks that things will be starting up, and then I'll help introduce you in a few minutes.
Okay. Oh,
cool.
Good to you.
Are you ready for the screen share?
Yeah, sure.
All right, I am making you the host. All right, you are the host if you want to do the screen share.
I think I am. I'll try it again.
Confirmed. There we go.
Great. Hey everyone, for those who are just joining us, we're gonna wait a couple more minutes, let some people trickle in. In the meantime, if you wanted to say maybe where you're from in the chat, be a good way to introduce yourself. And we'll get started again in just about 3 or 4 minutes.
Okay, Matt, would you like me to introduce you, or do you want to give folks a few more minutes here?
I think it's 5 after the hour. We should, out of respect to the folks who are here, we should go ahead and get started.
Great, let's go for it. Let's see if I can start video for this part. Hi, folks. This is Leo, founder over at Graphistry and helping organize Rapids Academy. I want to introduce Matt, would you like me to
Classic live stream fail, Leo.
Exactly. That's
I'm gonna stop sharing just so you get your full face here for a second.
Awesome. All right, thank you, Matt. So yeah, I'm pretty actually excited for this one. It was a long road to get here. I'm excited to introduce both Matthew Rockland, who's founder of Coiled, but if you haven't heard of them, you've probably heard about a project called Dask. Maybe you've used Rapids before. He was over at NVIDIA beforehand. And we also actually have a surprise guest, Ben Zaitlin, over from NVIDIA. Actually, I'll let you two introduce yourselves, but everyone gets a bit of a 2-for-1 for this one. With that, just as a bit of housekeeping, if you're on the YouTube, I encourage you to check out the Rapids Slack for either for now or after the session, and the Rapids Academy GitHub, where we try to share notebooks, all the try it yourself stuff. And then the last bit is I'm also excited to announce the next speaker, who will be John Murray, who is one of the earliest Rapids users and
Cool.
has been very heavy GIS and machine learning stuff. So with that, I'm going to hand the reins over to Matthew and Ben.
Yeah, great. Thanks, Leo. So hi, everyone. My name is Matt, sort of an active open source software developer in the Python space. I mostly think about scalable computing, or just how do we sort of scale up NumPy, Pandas, scikit-learn, and now Rapids. I mostly think about that in the project Dask. And I'm joined here today by Ben, who does all those same things. Ben, do you want to quickly introduce yourself?
Yeah, hi, everyone. I'm Ben. Thank you so much for coming. I also work in the Dask space. Matt and I have been friends and colleagues for a long time.
Immemorial, I think, is the right term, Ben.
That's right. Yeah, and now I get to do open source things at NVIDIA, trying to bring PyData onto GPUs.
Okay. So also a bit of housekeeping. So I apologize. First, I was supposed to do this last week. I was super swamped. I apologize to you all again. So usually these sessions have a really great structure where it's half of a talk and half of an interactive lab session. I have to admit, I did not get the lab session done in time. So this will be just talk. We can do extended Q&A afterwards. We're launching right now, and it's a really interesting time. Just this sort of fell by the wayside. But rather than delay further, we thought we'd give some stuff to talk about, and then in the future we'll give some session in a while. So with that, I'm going to share my screen again. And we're going to go through some slides and through some demos. I'm going to talk first, mostly about sort of Dask and scaling out multiple machines. Then we'll hand off to Ben, who will then go into sort of a lot of the challenges around managing GPUs in particular on many machines, and there are a ton of interesting challenges. And then Ben will do some other demos, and then we'll close out or open for questions. Okay. Again, if people have a moment just to introduce yourself in the chat, it's kind of fun to see where people are from. Maybe you can say your name and where you're from, the city that you live in, maybe. It's just kind of nice to see everyone who's around the world who engages in these sorts of activities. Okay, so we are here to talk about multi-GPU computation. If you haven't seen them already, I recommend looking at the previous talks on single GPU with Rapids, and then, sorry, there's Graphistry with security stuff, then there was single GPU Rapids, and then there was single GPU out of core with Blazing. Now we're talking about what happens, how do you manage multiple GPUs at a time? So we're going to assume for this talk that you have access to many GPUs. There might be one machine with lots of GPUs. These are pretty common these days. Might have 4 or 8 machines. It might also be several of those boxes all in a rack. Or you might just have a cloud account and you rent GPUs by the hour. We're also assuming that you want to solve data science and machine learning problems. These might be anywhere from sort of ETL problems you find with Rapids to solving machine learning problems with things like XGBoost, gradient boosted trees, or deep learning. Again, all spread across many machines. So this is sort of the camp that we're thinking you are sitting in. We're going past the situation where you have a gamer laptop. This is a bit more of a production situation. So what we've seen in the past couple of talks is that there's this Rapids ecosystem of projects which builds on the existing PyData stack of projects like NumPy, Pandas, scikit-learn, XGBoost, deep learning libraries, and provide GPU-accelerated variants of them. We've seen that those provide incredible speedups. You get all the power of CUDA programming of GPU-accelerated hardware, but without needing necessarily to understand how CUDA works. You can write sort of normal Python code and get that same level of speed up, assuming you're limiting yourself to some of those common APIs. So that's all well and good for one GPU. How do we use many GPUs? Right. So we've already solved this problem with CPUs in the past, right? So we can look at how we did that before, and that's what I'm mostly going to talk about. And we solved that problem historically with Dask. Dask is taking the existing CPU ecosystem in Python and effectively scale it up to many machines. Then we're going to talk about how we can do that exact same process with GPUs and see that mixture. So I'm going to talk for a little bit about Dask. Dask is a Python library for parallel computing, which was originally designed to scale libraries like NumPy, Pandas, and scikit-learn, but was then used to scale lots of other systems like Rapids or other internal systems inside of large companies. It's relatively easy to use. You probably already have it installed. It comes default with Anaconda. And it's also secure and trusted by very large institutions. So it's scalable both in technology sense and in a cultural and enterprise sense. So Dask provides parallel variants of common PyData libraries like NumPy, Pandas, and scikit-learn. And it does so by wrapping around those existing objects. So one Dask array is just many NumPy arrays. One Dask data frame is many Pandas data frames. And then it provides APIs around that, which use all of those many data frames either on one machine with lots of CPUs or GPUs, or on many machines across a cluster. Now, what we're going to see here is that, so look at the sort of maybe the Pandas image in the middle. You see that there's one Pandas data frame for every month of data. And we can split that up and swap out Pandas for cuDF in the future and do the same trick. And so everything we're about to see with Dask on many CPUs will also apply to what we're going to talk about later in the talk with many GPUs. So you can think of Dask as sort of a Hadoop Spark for Python, but actually it's much more of a tool to build things like Hadoop or Spark. And that's why we've used it when building out the Rapids multi-GPU setting. So because Dask has been flexible enough, it's sort of easy to plug into GPU accelerated workloads. So we've seen some use cases of this, things like Dask data frame, things like Dask array, things like scikit-learn. I'm actually going to switch out of talk mode for a second and play in a Jupyter Notebook just for a moment to talk a little bit about just showing you how Dask works. And we're talk also about metrics and about swapping seamlessly between environments. So before we start with GPUs, before we start with Rapids, before we start with Dask, we often start just with a small sample of data in Pandas. If Pandas works for you performance-wise, you should use Pandas. None of these projects are trying to displace Pandas in the sort of small data, fast computation sense. But eventually, you will need to scale out if you're working with larger data sets. And so here we're playing with, I'm going to spin up actually this Dask on a local machine. You can do this yourself. Dask is, again, probably installed. All of this is available by default if you're running Anaconda or if you pip install Dask. So this is the, I think, NYC taxi data set. We've played with this before on the Learn Rapids talks. And here with Pandas, I just read in 10,000 rows of one file. But with Dask, I might want to look at lots of data all at once. And actually, because I'm screen sharing, I'm actually going to scale my cluster down a little bit. So Dask went and found that my machine had 12 CPU cores, and it split those into 4 different processes. I'm actually going to scale that down to 3 processes. And you can see in the lower right here, my sort of cluster diagram will change a little bit. I'm going to switch down to 3 just so that my screen sharing technology can also have a core or 2 and things don't stutter too badly. And so what Dask does is Dask gives us the ability to chop up large data sets into lots of small chunks. And then it gives us the ability to schedule those chunks on lots of parallel hardware. And so Dask is doing that, and a bunch of work is now spinning up on my 9 cores of my local laptop. And you can see that here, where every line here corresponds to, again, one CPU core and what they're doing over time. So it looks like we are parsing some CSV files. We're then writing to Parquet. So this is sort of a standard ETL workload. This is going to go on for a while. And this is nice, though. I get to use my entire machine, my entire CPU machine, running this on my laptop, and get sort of full access. Now, in a bit, towards the end of the talk, we're going to swap out CPUs for GPUs, and each of these bars is going to correspond to one GPU that we're going to compute on. This is taking a little while. I'm going to stop. This would finish, though, nicely, and I'd be fully efficient with my local hardware. What we then want to do often is we want to switch from working on local machines. Here we use the Dask local cluster just to allocate as much computation as we could on my single machine with a bunch of CPU cores. And that's a very convenient way. So Dask works in this way. We always create a cluster attached to some hardware, and then we connect to that cluster and then run computations on it. What's nice is you can swap out that cluster to achieve different kinds of hardware performance. So we're going to switch from a local cluster to something running on the cloud. Here I'm using Coiled, our product, but you could use Kubernetes or AWS or Yarn or any other system like that. And we're going to wait, a little bit and wait for some cloud resources. It usually takes about a minute. And we're going to see that we can scale up to a much larger data sets by swapping our hardware. I want to call back for a second and say that it's convenient that we were able to go from pandas on a single machine and operate locally, then to scale out to Dask with CPUs on a single machine, and then use all of the hardware attached to that machine. And then we can scale out even further to now a cluster in the cloud. So I'm going to swap from my local machine to my cloud machine. And we can see here that I've got a few workers. There's more coming in, as you can see. And now we can start working, not with my local data set, but I can actually compute on this data set directly in the cloud. And now again, rather than working with the 9 cores of my laptop, I've got 100 cores or so on the cloud. And so this is the kind of experience that we like. We get to do the same workload, more or less, but swapping architectures. And that's what Dask has allowed, going from pandas to pandas plus Dask to pandas plus Dask plus the cloud. And that's also what we're going to allow when we switch to GPUs. We can do the same semantic workload, but on different kinds of hardware, on different architecture. Okay, so that ran. It's pleasant. It ran a lot faster. We worked on a larger data set. It was smoother, and now we get to close. And that whole computation cost me about 10 cents to run in the cloud. But it's also really quite slow. So if we take a look at what took time, so this is a flame graph plot. Dask does a bunch of statistical profiling all over code. And the majority of time that we spent is here. We're in pandas. We're parsing data. So this is the CSV parsing bits. Looks like this is I/O. So I'm seeing things like read into, socket, SSL. This is all network traffic. There's things here like also network traffic, it looks like. And somewhere around here, there's also some Parquet work. Yeah, so here's some Parquet work. But the majority of time is spent mostly parsing CSV files, a little bit of writing Parquet, and some network traffic. If we wanted to speed this up, the biggest thing to fix here is parsing CSV files. CPUs and pandas have kind of maxed out a little bit. How do we accelerate that? How do we go faster? That's where things like GPUs can come in. For this, even this, a very simple and trivial workload. So I'll switch back to slides. So it's also worth pointing out here that Dask and Rapids and Pandas work well on Pandas workloads, on tabular ETL data science-y workloads. But all the things we're going to talk about also apply to multidimensional data. Maybe you're looking at biomedical imaging, or you're looking at large simulations coming out of oil and gas problems, or looking at the weather or climate modeling. They also apply to systems like traditional machine learning with scikit-learn. So Dask integrates with lots of the scikit-learn APIs and gives you a lot of scalability. Or arbitrary task graphs, right? So Dask is really much designed around enabling many high-level APIs, providing parallel infrastructure around them, and that then schedules onto hardware. And many people have built lots of different APIs around Dask, which is very fun. A notable one of which is Rapids. And Dask handles scalable computing. Okay, we just saw an example. We're going to go past that. If you want to see more examples about Dask on CPUs, I recommend taking a look at examples.dask.org. That'll give you a sense for how Dask works internally and the kinds of things you can do with it. Now I'm going to swap out pandas for QDF. And we're actually going to swap over to Ben. Ben, if you're ready to start presenting soon. So everything we saw with Dask data frame and with pandas, we can also switch now to QDF. Right? QDF allows us to swap out wherever we were using pandas before, we can now use QDF to get GPU acceleration. The same trick of just combining all of these sort of single machine data frames into a big multi-machine data frame with Dask, that same trick will work well. Ben, you ready to go?
Yeah, I think you have to make me presenter to share my screen, right?
Oh dear. Well, I will stop sharing. And then hopefully you can start sharing.
Leo, we might need a little bit of assistance from you. I think you might have to make me host in order for me to share. Oh, maybe not.
Give it a go.
The share screen button on the bottom screen. Apologize our technical dust, folks. Kind citizens of the internet. Great, you succeeded.
You could do GPUs, but video sharing.
Folks can see my screen correctly?
You're good to go, Ben.
Okay, great. Thanks for that, Matt. Yeah, so we want things to be that easy, but actually it's a little bit more complicated. And the goal of Rapids, the goal of my team and myself is actually trying to replicate all of, or as much of as possible of PyData onto the GPU. And in order to do that, we need to build new technology. We also need to resolve a lot of systemic issues within the PyData community and also within the GPU community as well. And we're going to get into that of how we're resolving those problems. So this GPU ecosystem is kind of complex, but it's also super fun. As Matt showed before, the buy-in for moving to the GPU is not just that you get a little bit of speed up. It's not 2x or 4x, but it's like 40x or 100x faster. So there's a strong motivation for trying this out or for moving to the GPU. This ecosystem, as I said, is complicated. And it's not just these individual libraries that work. It's not just PyTorch working on its own. It's not just doing XGBoost on a GPU on its own. It's actually all these things working together. So we need to figure out ways of how to get PyTorch to be able to move seamlessly back and forth between things that were cleaned up in an ETL step by Rapids and that maybe move back and forth with CuPy. Everybody has a different way of maybe expressing that computation, and people have their own thoughts on what is best for them and their workload. Maybe it's arrays with CuPy, maybe it's data frames with QDF, maybe they like the boosting, maybe they like the training that XGBoost has to offer and not so much what QML has, or they really like QML. There's lots of things that are there, just like the regular PyData community also has. Not everybody uses scikit-learn, though many people do. There's other machine learning libraries, but what underlies all of that is a common set of APIs and memory managers as well. So it's really hard to wrangle all these things. Yeah. So within the CPU world, NumPy and Pandas kind of set the tenor. They're sort of the bedrock of the PyData world. Everybody has agreed that NumPy, the memory layout of NumPy, and you find things like OpenCV using NumPy and also scikit-learn. And that's really great to be able to move back and forth between those libraries seamlessly. And we need to develop similar techniques within the GPU world as well. But on top of that, GPU architectures are a little complex. This is a DGX A100 system. It has 8 GPUs. It has 2 CPUs. There's a lot of complicated networking. There's complicated disk interactions. This is sort of like a cluster in a box. And this isn't just a specialty item. You can go and rent them from AWS. In fact, multi-GPU boxes are becoming more prevalent. And you can go to Azure, Amazon, Google. You can install them locally. They're more and more common, and it pushes, unfortunately, the user to now think a little bit about how the computation is being executed and how to make it as efficient as possible. In the CPU world, so yeah, you want to say something?
So Ben, when you say that looks complex, I think that looks terrifying.
Yeah.
And also, especially like programming to that. Like, I mean, if I have to like target every GPU and target every transfer, Like if I've got data on GPU 1 and data on GPU 7, like how do I communicate between those two things? Like, there's a bunch of different wires there.
Yeah, maybe
when
I
we
should.
first started this, it was a mess.
Yeah, that's a good point. Yeah, so actually maybe it's worth pointing out that so each one of these is labeled GPU 0 through 7, so 8 of them. There are these fancy interconnects called NV switch. There are these InfiniBand devices over here, these Mellanox NICs. There's 2 CPUs, as we said before. There's PCIe switches. It is a little terrifying compared to what we think of in the CPU world. It's just, I have a chip, I have some memory, and I have a disk. Maybe there's some fanciness around like L1, L2 caching or something like that, but most users don't think about that.
Well, even in a like distributed setting, I'm gonna think of CPUs. My mental model is I've got 50 machines, all of which are the same, and there's uniform connectivity between all of them. I don't really think about this sort of like odd network. Well, in order to get from A to C, you got to go through E first, unless you like go through G and then back through C again.
Yeah,
it's
that would be terrible if we pushed onto users that particular problem. Luckily, we have resolved those particular issues. But when people first start out, or when they were first starting out with these architectures, they did have to solve that for themselves. Like, woe is the C++ programmer that does not have the PyData community standing behind it. Who does have to work out all these things. Yeah, so how do you, so assuming no GPU knowledge, how would you solve for the problem of running on a particular device where I want to run on just GPU 0 or GPU 1? Well, the standard thing in for NVIDIA chips is to use CUDA visible devices. And this environment variable lets you define which one or multiple GPUs you want your processes to work on. This tool that we've written at NVIDIA that's open source called Dask CUDA manages this process for Dask, where it creates one process per GPU, and all the CUDA context creation is set up for you. You don't have to do that yourself. You just use Dask CUDA to spin up workers on each of the GPUs. Networking, as Matt was saying, can be quite terrifying if you actually start to think about how do I move data between GPU 0 and GPU 7, and there's lots of options to go through those things. We can move from device to host, then transfer over TCP and then back up, but that would be really slow. We can also move over these NV switches. That would be really fast, but I also have another option of using these InfiniBand Mellanox NICs, and I can go through that. Again, you don't have to solve those problems anymore. Dask and this other tool called UCX lets the Python community and the PyData community leverage all of that hardware for you and choose the most optimal path between 2 GPUs on a single machine or 2 GPUs on multiple machines as well. So we can't have GPU 0 on node 1 and GPU 7 on node 2 and navigate correctly to that path, or navigate that path correctly. We also have another problem of managing memory, that the CPU world is quite plentiful in terms of memory. I can get 1 terabyte of memory. I have, not next to me, but I have 100 gigabytes of memory next to me, which is really great. But Amazon and other cloud providers make it pretty straightforward for me to go and request more and more memory. And GPUs, as many of you here should be aware of, are resource constrained, that they are extremely computationally efficient, but we don't have 100 plus gigabytes of memory on a single GPU. So we need to have new techniques to push as much data into the GPU as possible and then spill without breaking our computation. Again, Dask solves these problems for us. We can spill excess data from device memory to host memory and then eventually to disk. And we can tune that as well. So Dask will make choices for you, but you as the users can still have control over when that happens. It looks like you want to say something, Matt.
Ben, there's a comment in the chat by one of your friends who says that the NV switch on a DGX A100 is 300 gigabytes per second unidirectional as opposed to 50 gigabytes per second. Can you guess who that person was?
Hi, Keith. Sorry, I'd written that slide as NVLink, and it was originally using the DGX1 architecture, not the A100. So yeah, we can get really, really fast by using A100s. As a plug, the A100 I think is only available on GCP, but I think that they're going to be shipping them out to lots of other places shortly.
If I could add maybe a small note here, when Keith and I first, or sorry, when Ben and I first joined NVIDIA, there were a ton of scripts around. There was all these sort of 100-line bash scripts that people had written to manage some of this stuff, usually fairly poorly. And it was always kind of a pain. Everyone had sort of cobbled together their own way of managing CUDA visible devices and of talking to different network interfaces. And none of those were particularly good. All of them were kind of janky. And it was not something that you could really hand to a Python user and really expect them to get it immediately. And that's where a lot of the work that we focused on was actually just in setting things up effectively. And that's, I think, where we're heading to in a moment, is just making that all really easy. Fortunately, you need to think about all these things. I'll hand it back to Ben maybe for that big hurrah.
Yeah, you don't have to think about these things. If you join the PyData community, it's really great. If you're going to be on your own and write it in C++, there's a lot to think about. To do CUDA IPC, you have to call into IB verbs if you want to use InfiniBand. There's a lot to do starting out from zero. Yeah, so to do easy GPU multi-data, just use, or sorry, to do multi-GPU PyData, we can just put everything together with Dask and Rapids. And this is what our team actually goes out and builds. We think a lot about performance. We also think a lot about UX. We want to make this as easy as possible. Our goals are not just, we are definitely performance driven as a top priority. The next one, or maybe right next to it, is actually getting this in the hands of as many people as possible. Accelerating climate science research, business use cases is just also kind of deep within our team's DNA. That it allows you, for me personally, I have a different experience when I can move when I can iterate on questions in the like sub 10-second range. I just have a different interaction between me and my brain in terms of like what I can, how quickly I can ask questions and get results. And that very tight loop of asking questions and then producing that computation quickly allows me to be a little bit more freer in thought. Sorry, that's a bit philosophical, but I like those things. I like thinking about, I like there not being a barrier there. If I have to get up and go get a cup of coffee, that makes me, it just is a little bit more of a roadblock in terms of me playing that I don't enjoy. So you can get, so all this can be launched very easily locally with local CUDA cluster, as you can see on the right. There's multi-GPU support for Kubernetes, and we also regularly build Docker images for Helm charts as well. If you want to spin up an AWS GPU machine on any cloud or locally, all of that is fully supported. So with that, maybe I thought I would run a few demos. Yeah.
That sounds great.
Yeah. Okay. So I have access very generously to a DGX2 cluster, a DGX2 machine. Sorry, DGX2 machine has 16 GPUs, each one with a Tesla V100. Each one has 32 gigabytes of memory. So it's a pretty powerful machine. So it's like two DGX1s put together. And we're going to see what it's like actually manipulating these libraries. So we're going to use local CUDA cluster like I showed before. We have a little bit of some operations here to configure UCX. UCX allows us to take advantage of accelerated networking devices. And here I've turned on NVLink. So this allows us to transfer data back and forth almost as at the speed of the size of the card. So we can dump a card like 32 gigs in less than a second from one GPU to another. What this is going to do is instantiate a worker on each GPU, where each GPU has an RMM pool just has a memory pool of 26 gigs. So what we'll see, actually, if I switch tabs, here I can see each worker, each of these red bars refers to a worker. We have around 430 gigabytes of GPU memory total across our entire cluster to play with. Create a Dask cluster, just like Matt was doing before. And in this case, what we're eventually going to do, this is just a toy example that Matt and I did in the past to simulate some genetic data. We're going to build some random numbers, and we're going to actually build these random numbers on the device. By giving Dask CuPy.random state, all these will be generated on device as opposed to on the host and then moved into the device. So you can see here that Dask actually knows that these are going to be CuPy arrays. We're just going to time how long this full operation takes. It should be around 30 seconds. So what you see here is just a lot of randints, Dask generating, Dask telling CuPy to generate a lot of random numbers.
I'm curious, what's utilization during that period? Can we see both of them side by side?
So in doing this, we can see we get these nice warm fuzzy feelings by inspecting what's happening on the GPU. Again, like this is just so great that PyData, the PyData world, has thought about these problems ahead of time. That as we become active users of these tools ourselves, we want to inspect live and build these dashboards to see what's happening on the device. We want to know that something's actually happening there. So with a bunch of random numbers, we can now compute an SVD. If you're not familiar with an SVD, that's okay. This is just a quick way of generating lots of tasks and moving data around the machine. So we can see all these tasks that Matt pointed out before. The red is data movement. This went a little bit too fast for me to actually talk about them. It feels weird apologizing for how fast GPUs are, but I'm sorry about that. I can rerun it again. Maybe I should rerun it again. So computed SVD, which normally takes like tens of minutes on a CPU in 13 seconds.
Right, so it's a 200 gigabyte SVD computed in 13 seconds. That's incredible.
Yeah.
Hey, Ben, just pulling back a bit, had asked in the YouTube chat, but can you share a bit about, let's say somebody has multiple GPUs or multiple GPU nodes. What does it take for one, if they have a piece of that hardware, how do they add it to their Dask cluster? Do you have an example of that or anything? Or like, do they need Docker? Do they need, like, what do they need to do?
So this is running just on bare metal. You could use Docker if you wanted to, and everything works also seamlessly with Docker containers. Many of the developers within the Rapids team actually prefer to develop on Docker. It allows them to control their the dependency management that they like. I prefer doing it on bare metal and with Conda, but you can do either one. So install the same GPU multiple times on your machine, and you should be good to go.
I think maybe the question, Ben, is like, how does one set up a Dask cluster? And how does one shift that for CUDA? Maybe I'll suggest that maybe I handle that maybe after Ben finishes up his demo. If you have other things to go, we'll do this. Then we'll talk a little bit about deployment, both with sort of the Dask sense and in the Dask GPU sense.
That sounds good. So this was sort of one example that used, we used Dask, we used CuPy, and we did a Dask algorithm, or an SVD across all these things, all on the GPU. So whenever we did these particular operations that happen inside of an SVD, all of those gets translated into CuPy equivalents, on-device equivalents of those, of what it takes to make an SVD happen. A transpose, some matrix algebra. Next, I wanted to, this is a little bit contrived, but we're gonna create a cluster similarly, a Dask cluster. Instead, I just wanted to show off that local CUDA cluster, we can define the number of GPUs we want. So by using CUDA visible devices, 0, 1, 2, and 3, we're saying only build a cluster of 4 workers on those particular devices. And if we look at the memory, we can see we're only occupying 0 through 4. In this example, I'm going to use XGBoost just to show that Dask and this GPU ecosystem kind of all play nicely together. I'm doing this with my hands as like playing nicely together, but you can't see it. We'll create some random data with scikit-learn. One thing that I noticed about this example, actually, that I just noticed now is that these are NumPy arrays. When we come to XGBoost, we're going to call GPU hist. That's going to move the arrays from host to device. Rather than having XGBoost do that, we could actually just do that ahead of time. This is where I get to show off maybe a little bit of live coding. So we can call math blocks. So as Matt was saying before, these arrays are distributed into blocks of NumPy arrays. And in this case, I'm going to call CP as array.
So CP here is the CuPy array, is that right? Like the GPU NumPy variant?
Yeah, that's right. So for every block, we're going to move from device to, or sorry, we're going to move from host to device.
And for folks not living in the GPU land, host being the CPU and device being the GPU. That one took me, I think, about 2 years to get normal on.
It certainly comes a lot in the Dask documentation, because the Rapids folks want to refer to things as host and device, but all the non-GPU users don't use that same nomenclature.
Yeah. So now we can see that we have a CuPy device here. So we've done that mapping. And now if I do some training on this data, this should go. We can see some things happening in our Dask stream. And we did an XGBoost thing. It all kind of worked nicely in this sort of smaller example. Usually the more exciting examples involve like a lot more code cleanup. And I just wanted to show things happening here that played nicely. All this works inside of much more involved examples. If you're curious about them, I recommend going to, if you search for Rapids and TPC-XBB, where we have been benchmarking against more involved in real world use cases. Yeah, you want to take over, Matt?
Yeah, I'll take over. I'll talk a little bit about setting things up. At the end of that, I'll probably also need your help, Ben, in pointing to the best multi-node, multi-G setup docs, which I imagine is a Helm chart somewhere. So yeah, so there's a great question about how do you actually set up, if you have many machines, how do you set them up? I'm going to give, like, again, the first, like, the low level view about how we do things internally. And then we'll, point to people about how they can actually do things in practice. In the same way that Ben talked about all the problems, we'll then talk about sort of all the low level bits first, and then play with the bigger things. So Dask is arranged as a centrally managed distributed system. So you need one central Dask scheduler, which coordinates all of the work. And then let's make a few of these. And then you need a bunch of Dask workers, which connect to wherever that Dask scheduler is being hosted.
And this is all pip install or conda installable, right?
Correct. Yeah. So again, if you want to pip install Dask, or if you want to conda install Dask, that works just fine. Because Dask isn't actually handling any of the actual computation, it can be pure Python without really slowing things down that much. It's just sort of the orchestrator. So there's no sort of fancy compilation. So yeah, so that works just fine. And then if I wanted to connect to that, I would open up any sort of Python session. I'd make a Dask client. I would give it that same scheduler address. Here, I'm running all of these things locally. But in practice, you could be SSHing to lots of different machines, and you could be, logging into each individual separate machine, starting a Dask scheduler on one, starting Dask workers and all the rest. Here we can see
maybe a quick pause on that. Like if just like a regular secure setup, would you set up a SSH key sharing for it, or just like it comes baked in and you just set up like a username password? Like how would that look like?
Yeah, that's a good point. So if you, one option is you can use the Dask SSH command, which does a lot of that stuff for you. And typically in that case, yes, you would have SSH keys set up. This is fairly common, especially if you just have a bunch of machines lying around. What is maybe more common is to use some other system that is designed to manage distributed systems. So this might be a system, again, like SSH, as you were talking about, but maybe also a system like Kubernetes or Slurm or PBS or a variety of other things. The Dask setup documentation has pretty intense docs about a variety of ways to set up Dask generally. But GPUs have this extra consideration though, in that you have to deal with lots of different GPUs, deal with CUDA visible devices, all the things that Ben just mentioned. Now, Ben got around that on a local system by using the local CUDA cluster command, which comes from the Dask CUDA package. So Dask CUDA is a great package to have installed if you want to use lots of GPUs and Dask on a single machine. And again, this is super common. People buy machines like the DGX, like what Ben talked about, but also other machines that lots of other vendors will produce, or even if you're just renting a machine on the cloud. This library also includes a different Dask worker variant called the Dask CUDA worker, which works exactly like the Dask worker, but now handles all the stuff that Ben mentioned. And so if you have a bunch of GPU machines, you're just not going to use Dask worker, you're going to use Dask CUDA worker instead. Or again, you can use systems like Dask SSH, Kubernetes, et cetera, all of which will allow you to swap out the Dask worker command for the Dask CUDA worker command. Ben, is there a good reference for like maybe the Rapids Helm chart if people want to get set up quickly?
Yeah, just posted it in the Zoom chat. So if you go to helm.rapids.ai.
Yeah. That being said, it is still a challenge to deploy Rapids on a distributed system. You can also buy this service from other companies. I'll go a quick pitch for Coiled. At Coiled, we manage these things for you. It can be tough. And so there are ways to do it ways to do it with open source technologies like Kubernetes or Slurm or Kubernetes. Or you can again have someone else manage it for you. But yeah, so this is, I'll also put this in the YouTube chat. And I'll put up the setup docs in the YouTube chat. Great.
Maybe as a question from post earlier in the chat, and this is triggered by multiple conversations that have been going on in the Rapid Slack and also in the Graphistry users, where we see folks like, for example, in finance working in fraud, or in security doing like real-time anomaly detection, or in IT doing performance monitoring. There's been a lot of interest in using GPUs for essentially line rate analytics and line rate streaming analytics. And so Dask has been kind of interesting in that space because the potential to do out of core and the potential to do multi-GPU and things like that. And this could go either to Matthew or to Ben. Do you have any sense of, in terms of like, per GPU bandwidth and latency, especially like, let's say you want to do real-time scoring, anything like that? Any sense of where Dask or Dask CUDA or anything in this ecosystem, like where they are, any sense of numbers, especially relative to the network speed, stuff like that?
Yeah, we can maybe both jointly answer that. I'm going to point, again, a few links I'll put in the chat. So Dask adds something like sort of roughly millisecond latencies on top of things. And Dask can operate in a fully real-time way. So we can sort of add tasks to the task scheduler as they're computing. A millisecond either sounds like a really short time or a really long time, depending on where you are in that pipeline. If you're doing high frequency trading, it's an eternity. If you're doing like IoT device analytics and you're like reporting something to a dashboard, it's instantaneous. Yeah, so Dask adds like sort of millisecond roughly latencies to things. But other than that, I think network speeds. Ben, you want to say something about network speeds or how close we can get to bare metal speeds?
I actually don't know. I think that we just, I know that this has been a major focus of the next Rapids release. In 0.15 will be streaming. I have not had a chance to play with it myself. My understanding is that it is, I mean, without evidence, that it is extremely performant. I would expect it to be more performant than CPU for many cases. So it's called Q streams that I'll also post in the chat, an example notebook.
Right, so there are a few different components to this, right? I was first started off with the administrator system that you're using, the scheduler. What latencies did that add? That's about a millisecond per task. Then there's a question of like, well, how fast can we put things across a pipe, right? And that's a UCX question. And we're within, I think, 10% of hardware speeds on that is my rough understanding. There's also the question of like, well, like, can we actually write down computations to do, online transforms? And that's another interesting question. There's a library called Streams, which handles some of that. You can have streaming data frames that you can feed data into from Kafka topics or things like that, and they will aggregate, streaming, group by aggregation, join kinds of computations. The Rapids team in Common Form has taken that same library and augmented it to now work with Rapids, making the QStreams library, which I think is what Ben is referring to. So Leo, you asked a really simple, straightforward question of does this work or what's performance when it comes to streaming data? And the answer is, as with all sort of large distributed computing systems, there are like 5 or 6 different things you need to think about. And that was our answer. It's this really complicated answer. But in practice,
depends where your bottleneck is.
Yeah, I mean, I always like to say, high performance computing is not about doing one thing well, it's about doing nothing poorly. Because we're going to hit that bottleneck. GPUs made everything very, very fast. And as a result, all of the other potential bottlenecks became a lot larger in comparison. And that's why the Rapids team spends most of their time thinking about networking or about deployment or about hosted device transfers or about disk IO. They actually don't spend a lot of time. Like, I think, Ben, you don't even know how to write CUDA. Is that a fair statement?
I have written CUDA.
You're gonna get him worried about his job security here.
I think Ben's
yeah, I mean, that is without a doubt. I'm not at NVIDIA to write CUDA. That's not what I'm doing.
But maybe Matt, like something you said there actually really resonated, which is I guess kind of what you're saying. It's not so much always the compute, which is what people might be thinking about, but it's actually the network, the IO, the transfers. And then that gets back to Ben's original architecture diagram and the numbers he was putting there. So for example, I think you initially showed like a network connection at 1 gigabyte a second or 1 gigabit, I think 1 gigabit a second. And then there's discussion of like PCI cards at, which used to be, I don't know, like 8 gigabits a second or whatever. But nowadays, for example, on the cloud, you can get like, 10 gigabit, 40 gigabit. For PCI cards, like they've recently been shooting up to 32 gigabits a second. So even on like a single or multi GPU node system, with all that focus on IO, it sounds like the Rapids team has actually been working on different aspects to actually saturate that. And then what's heartening from Matt's answer is then, well, if we saturate that to actually distribute the work, you're saying Dask only adds like per task about a millisecond. And the tasks are, you were showing these, multi-gigabyte chunks.
Yeah, but even that becomes a bottleneck eventually. Yeah, so I think early on in the Rapids effort, and I think Keith, who's again watching in the chat, can attest to this, like the first effort was just like get the Python API working so we can do single node GPU things and then run many of them at scale. That's kind of like the demo that I showed at the beginning of this talk. It was just, can I transform this data in an embarrassingly parallel way? But then as we transformed to more complicated workloads like database joins or like Ben's SVD, very quickly, the bottlenecks were all about communication. And we saw that a little bit in Ben's, if you want to go back in the video, Ben's little dashboard was a lot of red, it's a lot of communication costs. And so like, I think for 6 months or so, the entire Dask team at NVIDIA was focused 100% on communication. And then there's questions like, well, great, now computation and communication are fast. We're now running out of memory. How do we solve that problem? And so as you keep sort of stressing the system, more and more things become challenging. And the great thing about the whole Rapids ecosystem is that there's a bunch of people who are working to make all those things really seamless and to solve the most important problem at any given time. And the QStreams example is another good example of that, right? We can now compute really fast, we can communicate really fast, we can set it up pretty easily, but we needed APIs to handle streaming workloads, like what you were talking about. And so great, and I need to focus more on Python APIs. So going back to Ben's point of this is really a systemic problem, like the Rapids effort is really a systemic solution. And there's a bunch of different kinds of activities that are all happening at the same time to make this a holistically pleasant experience, so that you can just switch from using pandas to using GPU, Dask, InfiniBand on NVSwitch pandas without really noticing too much. And that's maybe the big sales point of Rapids.
Yeah. So actually, I've got one more here, and feel free to punt on this or whatever. But it's on that same vein here, and this is one that came out of I forgot if it was the last week's session or 2 weeks ago, something like that, where we're looking at going through examples of out-of-core processing. And so there's and one of the big things about the Blazing release somewhere around Rapids, somewhere between Rapids 12 and 14 was the beginning of out-of-core support, where even if you're on, let's say, 1 or 2 GPUs, but you have like 10 terabytes of data, it'll automatically stream in and out for arbitrary operations. And they just made, I think, their full SQL subset to work there.
Awesome.
Or that was my understanding. I could be totally wrong, but then the kind of question is like, well, let's say we start using Dask, right? And I don't know if you can share a bit about how to think about it and anything there.
Yeah, so Dask has been doing out-of-core for a very long time. Probably won't be as effective as Blazing is on SQL queries, is my guess. In general, like between Dask and Blazing, if you're doing SQL stuff, you should use Blazing. If you're not doing SQL stuff, you should use Dask. And what's beautiful is you can use them both at the same time. Blazing is actually the first Dask-compatible SQL engine, which is actually really exciting for Dask users. Yeah, so Dask has been doing out-of-core for a while. Actually, Dask started not thinking about multi-machine. It started thinking about single machine stuff, mostly with out-of-core workload in mind. If there is a way to compute the thing you want computed in some sort of streaming fashion, Dask will usually find a way to do that. That'll work with most ETL workloads, most group by aggregation workloads. If you're like joining 2 giant tables, Dask can do it, but it'll be slow. But yeah, for a lot of workloads, Dask is very comfortable chewing through hundreds of gigabytes of data on a local laptop. And we actually saw that with the New York City taxicab dataset when I first did my first demo. Remember, I started with pandas, I then went to Dask locally, and then went to Dask on the cloud. And that dataset I was working on didn't actually fit in my RAM. But if you watch my memory monitor during that time, it was only at like 2 or 3 gigabytes of total resident memory.
Awesome. And so just to make that crisp, so like any Dask, any cuDF primitive like join, group by, filter, the Dask cuDF would then therefore automatically chop that up for you and spread it across 1 or more GPUs. And between, if you don't have enough GPU memory, it'll put that into CPU virtual memory.
That's correct. Yes.
That is a heart relief for I think a lot of people.
Mm-hmm. It'd actually be really fun, I think, like how big of a data set could you compute on like how small of a computer? Like if we got some like a Jetson kind of board, but with a more modern architecture, like could we compute a terabyte of data on it? That'd be fun.
Yeah, maybe a variant of that is the new A100s, right? Where I think it's like you can split up the new A100. You could virtualize or you can somehow physically partition, I think 32 unit compute units. And so, yeah, how would that work with Dask? Would you just have like, can you assign different Dask schedulers to different compute units, or how would you think about that?
Yeah, so Dask doesn't think about GPUs. I actually would want to know more about how the A100 sort of self-partitions a little bit. Is it like a CUDA visible devices 1.1 or something? Ben, do you know how this works?
It's the same. It's not, but now that each GPU is tied to a NIC in a slightly different way, but it's a fully connected DGX1 essentially.
Sorry, I think what Leo's talking about is like fractional GPU support.
Yeah, like
Oh, I don't know.
or
Yeah,
something. Giving
I have not tested that yet.
Yeah,
I know
that
that you
was
can
sort of
set it
fun.
up in odd number, like 1/7 of a GPU can be requested.
Cool. I guess we will have a future Rapids Academy session, streaming and micro GPU.
Well, it's game changing because GPUs are great. They're really expensive. They're available on the cloud, but like really expensive on the cloud. But if you could rent like a fraction of one, that suddenly starts making more sense than a heavy CPU node. And that's what's really exciting, right? Is making these things more accessible. Yeah. Okay.
We'll say one other thing that within NVIDIA, I've had a number of conversations, and maybe you had this in the past as well, Matt, where people have not bought into Rapids and they're like, oh, I know what I'm doing. I'm going to do my like CUDA thing, my custom CUDA thing with just Python multiprocessing or multi-threading. And I know everything that, I know a lot about how CUDA context issues and CUDA visible devices. I'll set that all up. And then they kind of run into problems because even though they know a lot, it's still a little tricky to get right. And then once they do get it right, they're like, oh, well, now I actually am resource limited. How do I then solve, like they keep on hitting the same problems that we've already been down. And then eventually through that like experiential pain, they then eventually make the jump to Rapids and to Dask, that it already takes care of all of these things for you. And that Dask is flexible enough that they're not just forced into using just data frames or just arrays. They can build out custom computations as well that happen on GPUs.
Right. I think that's so folks coming. That's folks coming from the side of like, if you write a lot of CUDA, this stuff means you're kind of saying that like that this lets you scale out your CUDA. And I think for a lot of the folks coming more from the Dask or like scientific world, where maybe you're more doing Python, but you're curious about getting into the CUDA side, it's more of the reverse of like, you're used to all the niceness of the CPU world of like an operating system with virtual automatic garbage collection and virtual memory. And then all of a sudden you're talking about this, host versus device thing with like limited memory size. And it sounds, and the raw QDF, you still have to kind of worry about that stuff in practice. But as soon as you start doing the jump to Dask or Blazing, that's when you get back into not really worrying as much and letting the sort of host environment take care of it for you. I noticed we're coming out that hour, and we've already got like a CEO here for like more than an hour. So maybe it's a good chance. Like, I don't know if Matt and Ben, if there anything else you want to make sure that you kind of get covered on this session.
No, I think we're good. At least from my end. Thank you so much for hosting us. And yeah, look forward to engaging further. Hope people had a good time.
Awesome. Yeah, and so thank you, Matthew. Thank you, Ben. I didn't even know we were having Ben today, so that was kind of like a double win. So thank you on that. That was a great demo. For folks tuning in, or probably for most cases just watching after, a few quick notes. So again, Matthew represents the Coil team, and they're launching abilities to do a lot of management of the GPU stack for your own system. So just check out, I think it's coil.io. So check that out. For if you want to try some of this stuff yourself, we're going to try to work with the presenters to get the various notebooks shown in the GitHub. As well as they're showing actually some interesting add-ons and things, so like Jupyter extensions. So we'll try to get a list of those and have those linked in as well. Looking forward, we still do want to do a Dask hands-on. So we're going to see what we can do about that to make sure we do get a bit of that. In the meanwhile, for some of those things, I think you will be able to, and we'll include the links. There's a site, app.blazingsequel.com, where you can actually do a single, I think a single client Dask session. So you can try that out for free. And then the rest of the stuff folks were talking about to do the multi-GPU variant. And with that, I want to say thank you again to our special guests today. And thanks for tuning in. And oh, sorry, and the last bit here. We're still finalizing the exact details, but the next session will be with John Murray, who's one of the earliest Rapids users and very heavy in pushing the GIS or kind of mapping community forward, and also are more recently working at the intersection between GIS and machine learning. And so how do you handle giant, world scale satellite data, and then do like basically instantaneous, neural networks, things like that, on to actually make pretty brilliant insights on top. So that will be kind of the next talk and hands-on that we'll be targeting. So with that, thank you everyone, and we will catch you next time. And I think, Matt, you might be the host here. So I think you might be the one stopping the the current session.
And we're out. Bye, everyone.